The purpose of this lab is to examine how the momentum principle, also known as Newton's second law, functions by observing an object moving at constant velocity and therefore zero net force. This will reveal an aspect of how net force affects movement. To achieve this goal, a tracking software was used to examine a video of the movement of an object at constant velocity, comparing the observations of the computational model of the object's motion. We are under the assumption that there are no net forces acting on the object of our choice, in this case, a tennis ball. For the graphs of the models, I used position as the y-axis and time as the x-axis. I found that the observed path was linear and did not travel as far as the theoretical model, as the slope was less steep. The theoretical model also traveled linearly, as we would expect of an object at constant velocity. This is the expected result, as no net force implies that there is no acceleration to cause the ball to speed up or slow down, which would cause a curve in the graph's line. Flipping the axes would not change the linear relationship or the downward slope of the line, but it would imply that time is a dependent variable, meaning that an increase in distance causes a time to increase. I hypothesized that the observed model did not perfectly match the theoretical model because there were sufficient outside forces to make the net force non-zero. Friction at both the surface and at air resistance are the most likely candidates, though the ball could have drifted, though I believe it traveled in a straight line. This would have accounted for some of the discrepancy between the graphs. This is how I created my theoretical and observed models. For my observed model, I imparted initial velocity on a tennis ball and recorded its movement with the assumption that friction would be negligible to the object in rolling instead of sliding. To improve the experimental model in order to decrease the discrepancy between the models, there are ways to decrease friction. Ideally, the object would be given an initial velocity in a vacuum to remove air resistance, and a smoother object and contact surface would be chosen to reduce surface contact friction. For example, a smooth steel marble could be chosen as a rolled object, and smooth ice as a surface. A track could also be laid out to keep the ball from drifting, but that would increase friction. With these steps, the experimental model could approach net force of zero. Of course, we can't determine that friction and the initial force applied on the ball were the only forces acting in the observed system. In fact, we can't determine the number of forces acting on the ball to give us net force at all. There could be a variety of forces invisible to the naked eye, ranging from something like a breeze to some electrostatic force built up on the ball's surface. We can only assume that the net force is close to zero due to the linear relationship between position and time that we observe in the graph. This is my code that I used to create the theoretical model. As you can see, we have the ball's position, initial velocity here, described in ball.pause and ball.vel. And then in this while loop, we control the movement of the ball through its updating position. We update the ball's velocity here and position here by multiplying the ball's velocity times the time step and adding it to the ball's current position. Same thing with velocity, multiply the ball's net force divided by the ball's mass and multiply by time step and add it to the the current velocity. However, in this case, we assume that net force is zero, so we assign the vector value of 0, 0, 0 to the net force to match the assumption that we made of constant velocity or net force of 0. Through this experimentation, we confirmed that a net force of 0 is equivalent to a constant velocity.